Okay, so let us quickly recall the topics we have covered in the previous session. We defined what is an inner product. So inner product in Rn and Cn both are already discussed. So for inner product in Rn, we have symmetry. That is when you interchange the positions in the inner product, then the values are still the same, right? And they are linear in both the arguments. So they are bilinear. Bilinear in the sense that, so if you are having in a product AU plus BV comma W, then you have A times of inner product U comma W plus B times of inner product V comma W, right? And this is the linearity in first argument. And linearity in second argument means that you have inner product of U comma AV plus BW is equal to A times of inner product U comma V plus inner product B times of inner product U comma W. So you have linearity in both the arguments. Whereas in Cn, you see that even symmetry is not like here. So here you have conjugate symmetry. What do we call this? We call this conjugate symmetry, right? And the linearity in first variable is there, and we have conjugate linearity in the second argument. What does it mean? So inner product of U comma AV plus BW is equal to what? Can you complete? Is equal to A bar inner product of U comma V plus B bar inner product of U comma W. Is that correct? Yeah, do you?
Yes, ma'am.
Okay. And what is mean by norm of u comma v? So norm of u comma v represents the distance between two vectors u and v. Okay, so that can be visualized from here. And what are orthogonal vectors? We say that two vectors are orthogonal if inner product u comma v is 0. Okay, so geometrically we are considering that two vectors are orthogonal if they are perpendicular. Okay, and the zero vector is orthogonal to all vectors. Okay, and what is the vector perpendicular to itself means what? So you have inner product of v comma v is equal to 0. This means that this happens if and only if v is equal to 0. So this is the positivity condition you have here, right? The positive definiteness is there for both Rn and Cn. So because of the positivity condition, if you have inner product v comma v equal to 0, this is possible only when the vector itself is 0, right? And then you have the Pythagorean theorem, which says that norm of u so whenever, so this condition for Pythagorean theorem is very much important. Without this condition you cannot have the Pythagorean theorem. So if you have two vectors which are perpendicular, then norm of u plus v whole square is equal to norm u square plus norm v square. Okay, and then you have the orthogonal decomposition. So given any vector u, you can decompose it as cv plus u minus cv, where these two vectors are orthogonal. So if this is u1 and this is u2, then you know that u1 is orthogonal to u2. Okay, and how to find such a v? So just from the properties of inner product, you know that if these two vectors are perpendicular, then the inner product is 0. So from this you know that c is given by this value, that is inner product of u comma v by norm v square. Okay, and then we saw what is Cauchy-Schwarz inequality, which is modulus of inner product u comma v less equal to norm u into norm v. Okay, and then you have the triangle inequality, which says that norm of u plus v is always less than or equal to norm u plus norm v, right? And then you have the parallelogram identity, which says that norm of u plus v whole square plus norm of u minus v whole square is equal to 2 times of norm u square plus norm v square. Okay, so these are the things we are having, we have seen in the previous session. Okay, so I guess we have done this example already. So yeah, and then we also saw what are orthonormal basis, right? So you will say that your given set of vectors is first of all orthonormal. First of all, they need to be orthogonal, and then norm of each of these vectors is equal to 1. So usually the way it is represented is like this. So whenever you are having some set like this which is orthonormal, then usually we say it like this. So inner product VI Vj is equal to 0 if I not equal to j, and 1 if I equal to j. Okay, so this means that the set of vectors are orthonormal. Okay, and if you just have a set of orthogonal vectors, then you can easily convert it to orthonormal by dividing each of the vector by its norm. Okay.
Ma'am,
Yeah.
can you just tell what is like orthonormal? Why we make these vectors orthonormal, and if we are making them orthonormal, so is it like canonical basis or something?
No, it's not canonical basis. So I have given an example, the Hadamard basis example, and I guess from this also we obtained an orthonormal basis, right? So orthonormal basis need not be canonical basis. So why are we obtaining this orthonormal basis? So as I told you in the previous session, so orthonormal basis plays a very important role in diagonalization. So when you are diagonalizing, particularly when you are diagonalizing some specific type of matrices like symmetric matrices or normal matrices, which we are going to cover in week 11 and 12. So in the spectral theorem, you see why this orthonormal basis plays an important role. Moreover, not just that in spectral theorem, even for simple things like I explained in the previous session, orthonormal basis is important because if you just have a basis expressing a given vector, finding the coefficients is quite hard. Even for a 2 cross 2 problem, it is going to take some time. So imagine for an n, or if you are having an fn and you are having like n vectors, so this n can be anything, n can be even 100. So how are you going to find the coefficients if you have to keep on solving system of linear equations, right? So to reduce that process, if you have an orthonormal basis, so the computation of the coordinates reduces to just this formula. That is another important observation you have when you are having an orthonormal basis. I guess I gave an example in the previous session, right?
Okay.
Yeah. All right. So, yeah. So let V1, V2, Vn be an orthonormal basis of Fn. So if you want to express any vector V of Fn using these vectors, then you know that the coordinates are simply in a product V comma Vi, right? So this is an important property of orthonormal basis. Okay, so with this, these are the topics we have covered in the previous session. Okay, so next we are going to look at what is Gram-Schmidt orthonormalization. So it means what, given any set of linearly independent vectors, how can we convert it into an orthonormal set of vectors? Okay, how can we convert into orthonormal set of vectors? So let us say you are having the vector v1 v2 vk, and this is a linearly independent set. This is given to us, these are linearly independent set. Okay, now how are we going to make this into an orthonormal set? First step is that you take this vector v1 and normalize it. So what is norm of u1 here now? What is norm of u1?
V1 divided by U1.
Exactly, what is norm of u1? I have already told about this yesterday.
So that would be 1, I guess.
Yes, right. So this should be 1, right? Because we are normalizing. When you take the norm, it is simply 1. Okay, and for j equal to 2 up to k, so wj is v. So wj, so here there is some relation. I don't know whether I have mentioned. Yeah, it is here. So here you first compute Wj. What is Wj? Wj is given by this formula. For example, what is W2? Let us write it precisely. W2 is V2 minus inner product of V2 comma U1 into U1. Okay, so then you find what is U2. So then U2 is simply no, W2 by norm W2. Okay, so first you are finding a vector which is orthogonal to u1. So w2 is orthogonal to u1, and then you are normalizing it. Okay, same way you find w3 etc. up to wk. Okay, and the important observation here is that span of v1 v2 vk is exactly same as span of u1 u2 uj. Okay, take any set of vectors, not the entire set, even take a small set like v1 v2 vj, then the span of v1 v2 vj is same as span of u1 u2 uj. Okay, so this is an important property of Gram-Schmidt process. Okay, all right, so this is
Ma'am,
just, yeah.
is there any way to visualize this?
Yeah, so as I told you, so whatever you have here, so these things are nothing but projections. So how are you getting these vectors? It is very much related to projections. We have not yet started what is projection. For now, we have just given a formula which can help us to convert a set of linearly independent vectors to an orthonormal vector. Okay, so once we see the projection, I may not be able to explain exactly what is going on using projections, but maybe I can give you a hint of what is what. Okay, so I can relate the formula here, how it is related to the projection formula, that I can show you. Okay, fine. Basically this part is nothing but the projection of u1 on v2. And you know that, so suppose you are having two vectors, so it is the same concept like we are having here, right? So suppose you are having a vector here, so this is the projection of u on v, you can say. So then you see that this u minus cv and this vector here, this v, they are perpendicular, right? So the exact same concept is used here as well. So this is the projection, and then this is the other vector v2, so these two are orthogonal. Okay, so you can sorry, the difference v2 minus this is orthogonal to u1. Okay, so maybe once we complete projection, I will come back here again. Okay, that way it will be more clear. For now, just understand the formula, and let's try to understand the formula with some example. Okay, after projection we will come back here. Is that fine?
Okay, ma'am.
Okay.
Okay.
Ma'am, one question, please.
Yeah, yeah.
This u1 at the end of the inner product, how are we multiplying that in v2 inner product u1, and then there is a u1 outside it? How are we doing that?
So that's what I'm saying. So you want the explanation of how we got this formula, right?
No, no. I just want to know how we are multiplying that u1 at the tail end. Is it another inner product, or what are we
No, no,
doing
no,
in
no.
here?
So, okay, maybe let's do a problem and then you will understand what we are exactly doing with this U1 here. Okay, that way I will explain it in a better way. So, let's try to understand it with an example here. So, we are given with a set of vectors. So, let us call them as V1, V2, V3 itself. So, let's call this as V1, V2, V3. Can you all first compute what is U1? Everyone, please compute what is U1.
It would be 1 by root 3 and that vector v1, and the second one would be 1 by root 2 and that v2 vector, and v3 would be 1 by root 2 and that v3 vector.
No, 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 no. So first step is just computing u1. Okay. So first we are computing what is u1. u1 is equal to just v1 by norm v1.
Yes, ma'am, that's what I told
Okay,
you.
this is fine, but after that you should not do it for all the vectors. Okay. So you have 1 by root 3, 1 comma 1 comma 1. Okay, so at this stage what is the observation we have? At this stage the observation is that span of u1 is same as span of v1. Okay, this is the first step. Okay, so this is just an observation. Okay, and then, so what's the next step? You need to find what is w2. So how to compute this w2, how to understand this step here? So you are having, what's the formula you are having? So the formula is w2 is equal to v2 minus inner product of v2 comma u1 into u1. What does that mean? So v2 is this vector 1 0 1. Okay, and inner product, remember that always inner product means it is just a number, right? So what is inner product of v2 with u1? What is the value of this? So this is nothing but what is v2? V2 is 1, 0, 1. And what is U1? U1 is 1, 1, 1. So this value is equal to 2. So 1 plus 1.
And we can write that 1 by root 3 later or together.
So see, 1 by root 3 is there for each of the components. So it is a product of all these things. So here maybe I can bring it out. So for easier computation purpose. Okay. So here you have 1 by root 3, 101, 111, which is 2 by root 3. Okay. So the value of this is simply 2 by root 3. Okay. So you have 2 by root 3, and then this u1 is, what is your u1? Again 1 by root 3 times of 111. Okay, so you are having 101 minus 2 by 3 times of 111. So if you further simplify, 1 minus 2 by 3, you will have again 1 by 3 minus 2 by 3 and 1 by 3. So do you understand now what does this expression here, this u1 means? So what you have to do, is that clear, Tanzil? Yeah.
Yes, thank you.
Yeah. Okay, so now I leave the next step to you all. Take your paper and pen. Write first the formula for W3. What is the formula for W3 based on this expression? Based on this expression, what is the formula for W3? W3 is
V3 minus V3, comma, U2,
hmm,
U2.
U2, and then minus, you have to continue till you get U1 at the last. So you have to again write v3 comma u1 into u1. So this u gets decremented, so at each stage, so you have first v3 and then here u2 and then u1. In the next, suppose you have to you have more vectors, then you will have like, for example, u4, u3, u2, u1. Like this you have to complete the formula till u1. Okay, so can you all complete and tell me what is w3? Everyone do the computation.
Ma'am, this is W3, right?
Yeah.
So we have to tell W2.
W3, W2 already I have computed. See, this is W2. Okay, so here if you want to find U2, you have to just find the norm of this vector first. So how do you find norm of this vector? Can you complete and tell me what is norm of norm of W2? What is norm W2?
Root 2.
Is it just root 2?
By root
Yes,
3.
ma'am.
So you have 1 by 9 and then plus 4 by 9 and then plus 1 by 9, the whole square, right? Square of each of this term. So this is actually square root of 6 by 9, which is square root of 2 by 3. Is this correct?
Yes, ma'am.
Yeah. And so what should be your u2? U2 is this vector.
1 by root 2.
So you have here root 2 by root 3, which becomes root 3 by root 2 when you are putting it in the denominator. And then you have 1 by 3 minus 2 by 3 comma 1 by 3. So this actually becomes 1 by root 6, 1 comma minus 2 comma 1 when you simplify. Correct? Is this fine?
Ma'am, but U2 would be V2 by norm of V2, right?
U2 is W2 by norm W2. Okay. U2 is W2 by norm W2. So this is your W2 and this is your norm W2.
Okay, ma'am. So that first formula will only apply to U1.
Yeah, that's what I said. You were saying for all vectors, you should not do it for all vectors. You should only use for u1 and then you find w2 and then you find u2 in this way. Okay. And then
Okay, ma'am.
every time write the formula so that you easily remember the formula.
Excuse me.
Yeah,
The V3 part is common to all the terms. So if
yeah,
we are taking W4, then V4 will be common everywhere.
exactly.
Okay.
So common in the sense it appears in each of these terms, yes. So what's the value of first of all inner product V3 comma U2? So this is your V3 and this is your U2. So you have 1 by root 6 commonly, and then you have 0, 1, minus 1, and then U2 you have 1 minus 2, 1. Minus 2 minus 1, so it's minus 3. So minus 3 by root 6. Similarly, what is inner product of V3 comma U1? Compute and tell me the value alone. Just inner product V3 comma U1.
Ma'am, 0.
Yes, so this part is 0. Okay, so now you can substitute each of these values. So W3 is V3. What is V3? V3 is 0, 1, minus 1. So 0, 1, minus 1, minus 3 by root 6. U2. What is U2? U2 is this vector. 1 by root 6, 1 comma minus 2 comma 1. So 1 by root 6, 1 comma minus 2 comma 1. And then you have minus inner product V3 comma U1. So which is 0, right? So you only have this part. So you have 0, 1, minus 1, minus 3 by 6, 1 comma minus 2 comma 1. So when you simplify, you have minus 1 by 2 and then 1. So minus into minus here, this becomes plus. So plus 1. So 1 plus 1 is 2. And then this part is minus 1. And here you have minus 1 by 2. So minus 3 by 2. Is this correct?
Yes, ma'am. Uh,
So I missed one minus symbol here, I guess. Right? So here is already a negative sign. And then you have minus root 3 by 6. Right? So this should be actually plus if I'm right. Yeah. So this,
Yes, ma'am.
in that case, this will be 1 by 2 and this will be 1 minus 1. So this will become 0. And then this is minus 1. And then here plus 1 by 2. So minus 1 by 2. So 1 by 2 times of 1, 0, minus 1. So now this is just W3. Now how do you compute U3? What is the formula for U3?
W3 divided by norm W3.
Yeah, so what is norm W3? 1 by 4 plus 1 by 4 square root of
1
1.
by root 2.
Yeah. So what should be your U3? Your U3 is this is your W3 and this is your norm W3. So what's your U3?
1 by 2
1
root
by 2
2.
root 2.
1 second.
1 by 2 or 1 by root 2, right? Because you have another 1 by root 2 here, so it comes to the numerator. So you will have actually 1 by root 2 and then you have 1, 0, minus 1. Is that correct?
Ma'am, it will be okay, ma'am. Yes.
Yeah. So again, there is something we need to observe at each step. So what is the observation we are having? So observe that span of u1 u2 is same as span of v1 v2. Similarly, here you observe that span of u1 u2 u3 is same as span of v1 v2 v3. See, you cannot simply take, for example, u1 u3 equal to v1 v3. That is not possible. So you have to take them to everything in order. Then only this spanning concept will work. Okay. So now what are the vectors we have obtained? So the final answer. So the final answer here is u1 is, what is your u1? It is 111 root 3 you have. So 1 by root 3 times of 111. And then what is your u2? Your u2 is 1 minus 2 1 by root 6. And then here you have 1 by root 2 1 0 minus 1. So these are your orthonormal vectors. Is it easy to verify that they are orthonormal? Just take 1 1 1 and multiply, do the inner product with 1 minus 2 1, so you get 1 minus 2 plus 1, so 0. Same way this is also 0, this is also 0, so the inner product with each of them are 0, and each of them is having norm 1. Okay, so this is the final orthonormal basis which we have obtained. Okay.
Okay, ma'am.
Okay, so how to apply this formula, is that clear for everyone? Yeah. Okay. So
Yes, ma'am.
now, okay. So now, so since any given set of vectors can be converted to an orthonormal vectors, so for every subspace of Fn, there exists an orthonormal basis, right? Because for every subspace, you know that you have a basis, and that basis you apply Gram-Schmidt, right, and convert it to an orthonormal basis. Okay, so for the subspace you always have a basis, that basis you apply Gram-Schmidt and convert to an orthonormal basis. In that way every subspace has an orthonormal basis. Is this part clear for everyone? Yeah. Why every subspace has
Mm.
an orthonormal basis? Yeah.
One part is not clear.
Which part?
When we made this orthonormal basis,
Hmm.
we are saying it is related to our original basis because the span is equal to that
Yes,
of the
exactly.
original basis.
Yes,
Um, so does that mean this new ONB that we have made is very specific to our original basis?
exactly. That's why, see, whatever basis you are taking, so suppose you are having W, so and you are having some basis for W, so W is your subspace and B is your basis of the subspace. Since when, suppose let us say the B dash is your orthonormal basis which you have obtained using Gram-Schmidt, then you know that B dash is also a basis for W because of the spanning property. Okay, because of this spanning property, this the basis you obtained from here is also a basis of this exact same subspace W because of this spanning property. Clear? Yeah.
And also, if we take some other basis called C,
Hmm.
then we will get an ONB called C dash, and it will be very different from B dash.
Yes, it is going to be different from B dash, but the anyway we are going to have the span of all these vectors is coming back to our W. Since we are having infinitely many bases, again infinitely many orthonormal bases as well. Okay, each of this basis is going to give us a different orthonormal basis. Clear? All right. So how many of you remember the Schur's theorem, like upper triangle, like for any operator T from Cn to Cn, first of all you know that T can be made upper triangular. Is that part Can you all remember? Do you remember this part? That for any operator t from Cn to Cn, you have a matrix representation of t with respect to some basis where this matrix representation is upper triangular. Is that part clear to everyone? We have covered, I don't remember exactly in which week, but this is already covered, I remember. Yes?
One question I have in this,
Yes.
in the quiz we had this question, and there was a specification over there that that is only true if the matrix is real. But here we are talking about Cn, so I'm kind
Yeah,
of
yeah,
confused.
yeah. So that is a catch there. See, when you are having Cn to Cn, what was the difference between Rn and Cn? Suppose you are having T from Rn to Rn. Okay, so even let's take a very specific case of R2 to R2 itself. Okay, even for a 2 by 2 case, what happens? So we may have real values, but it is not necessary that always they are real. Suppose when we are having complex eigenvalues, then we have some problem. Okay, when we have complex eigenvalues, then the eigenvectors may also be complex. Okay, and complex eigenvectors, then what the problem, what the statement given in the exam was that you were given that for t you were having that the given set of bases is also from R2 or Rn, which is not true. So here the eigenvectors can be complex as well. That is where the problem was in that particular statement, and that's why it was false. You understand why this is different from this when it becomes R? Because here the basis can be complex vectors. So in that case, the statement in the original question was mentioning that you have a basis consisting of real eigenvectors. That's why the statement was false. Do you understand?
So because our eigenvalues have gone outside the field,
Yeah,
we are not able to put them in the upper
exactly.
triangular.
Exactly. Okay, we can still put it up as an upper triangular. See, upper triangular is not the problem here. The problem is the basis is not in Rn. That's the problem. Upper triangularization is still possible. Only that the basis is not in Rn. It is in Cn. Okay.
So the matrix of the basis, basically, the
Mm-hmm.
eigenvector basis has gone out of the field, but
Exactly.
that problem is not there in Cn because we are already in that field.
Exactly.
We can
Exactly.
get complex vectors, no problem. They are already part of the field.
Exactly.
Okay.
Okay. Fine. So what was that? So we know that we can always find a set of vectors which are so let us say you have t from Cn to Cn. What is known to us? It is known to us that we can there exist a basis, or let's not use notations, I'll write there exist. So there exists a basis of Cn with respect to which the matrix of T is upper triangular. This is what we already know. Okay. Now we already have a basis of Cn. Now you apply Gram-Schmidt and convert into an orthonormal basis of Cn, and then we get the Schur's theorem. Okay, there exists an orthonormal basis with respect to which the matrix of T is upper triangular. Is this clear? Yeah?
Yes, ma'am.
Okay. All right. So,
So not only can we have this basis with respect to which we are able to make the matrix upper triangular, we can also form an ONB form of that very basis, and that will still be giving us an upper triangular.
exactly. And one advantage of having this ONB is again that so when you are having an orthonormal basis of Cn, so how do you get this matrix T? Do you remember? So you usually suppose, let us say the basis vectors are v1, v2, vn, right? Then how do you get this matrix? If you remember, so you take the matrix P where the columns are v1, v2, and etc vn, right? And you get this the matrix, suppose A is the matrix representation, matrix of T with respect to canonical basis, right? Then what do we know from the triangularization property? That A is equal to P inverse dp, not dp, maybe d is like diagonal, so maybe I'll use something like, I don't know, bp, so where b is of the form lambda 1, lambda 2, lambda n. So this part is 0 and you have some entries here. It's an upper triangular matrix, right? So B is of this form, right? Now, if this P, if these vectors, so let us say you are having a Q where you are having now, instead of this V1, V2, Vn, you are having the orthonormal vectors. So let us say the orthonormal basis is U1, U2, Un. Okay, so this is the basis and this is the orthonormal basis. So here you have the vectors U1, U2, Un. Okay, so this matrix is now an orthogonal matrix, and for orthogonal matrix, what is P inverse? I mean Q inverse. Q inverse is same as Q transpose. Okay, so that reduces a lot of computation again. Okay, so when you have an orthonormal basis, then in that case the matrix, the inverse of the matrix is simply the transpose of the matrix. Okay, so this is again an advantage of having an orthonormal basis. Okay, fine.
Just one question.
Yeah,
Isn't it P, B, and then P inverse at the end?
yeah. So I don't know exactly. So when you write it as like D is equal to PD, PAP inverse, so their inverse comes on this side, and when you write A here, then P inverse comes this. It depends on how you are writing. So whether you are writing the diagonal on this side or A on this side, so that is how it varies. If I remember correctly, that is how it is done, I guess. I don't remember exactly in which week I can refer to it. So this is how usually we write. I guess.
My approach is that since the P matrix, V1, V2, and all that, they are
Mm-hmm.
the vectors of V written in canonical coordinates. So
Hmm.
when we multiply that P matrix with B, we'll again get canonical coordinates. So by that logic, it should be PBP inverse, is what I was thinking.
See, either way, you are going to get a diagonal matrix. That is not going to change. But I don't know what was the notation used in the mm, class. So let me maybe quickly check for what's the notation. Just give me a minute so I can even write exactly the same format instead of writing something different. Just a minute. So yeah, M is equal to PDP inverse. Yeah. Fine, fine. So I guess what you are saying is correct. So in the class we use this notation that. mm, Okay, so it is something like this. So here, anyway, so for the inverse part, you don't have to calculate the inverse. You have Q inverse is equal to Q transpose here. Okay, is that fine?
That property Q inverse equal to Q transpose,
Hmm.
is it true for orthogonal system or orthonormal system?
This is true for orthonormal system. For orthogonal, you won't have this. Okay, this is because when you have an orthonormal system, what happens because of the inner product property, what you will have is that Q into Q transpose is equal to identity. Because of the orthonormality, you know that, as I told you, inner product ui uj is equal to, simply you have 0 if I not equal to j and 1 if I equal to j. So in fact, the entries of Q into Q transpose are simply inner product ui uj, ui comma uj. That's why you get it as identity matrix, and then you have this property. Do you see what's going on? Yes.
I'll have to multiply that out to see what's going on. But for now, orthogonal will fail this test, but an orthonormal one will pass
Mhm.
this test.
Yes, yes. See, there is nothing to multiply. You can visualize. See, this is U1, and for Q transpose, your U1 is going to be here, right? So you have U1 here, and for U transpose, the first column is your U1 now, right? Sorry, first row is U1. So now when you are multiplying, you have first multiply this with this. So it is exactly inner product of U1 comma U1. So in that case, the first entry will become 1. So in that way, you can visualize or imagine without even computing. Okay. If you want, yeah, of course, you can write and see that the entries of this QQ transpose are basically inner product UIUJ. Okay. All right. So next, we are moving to orthogonal complements. Orthogonal complement is something which we already know as a concept, but we don't know the terminology, right? For example, here we in this example find all the vectors in C3 orthogonal to both 1 I 0 and 0 I 1. So here, what did we do? So let us say this is your vector V1, this is your vector V2. Okay, and let us say W is equal to span of V1, V2. Okay, now so let us say v3 is the vector which is orthogonal to both v1 and v2. So v1 v3 is 0, v2 v3 is 0. So v3 is the vector perpendicular to v1 and v2. So this implies that v3 is perpendicular to w for any w in this subspace w. Okay, and what is mean by orthogonal complement? So in this case, orthogonal complement is simply span of v3. Okay, so in this case maybe you cannot visualize, but let me give another example where you can easily visualize this orthogonal property. For example, suppose you are having, let us say v1 is 100 and v2 is 010. So what is the span of v1 v2 exactly? Can you quickly say what is span of v1 v2 exactly in R3? This w is basically your,
XY plane.
yes, this is your xy plane. Okay, so without even computing what is the vector which is orthogonal to these two vectors, you automatically know which vector is orthogonal to this v1 and v2. What are all the vectors?
The Z axis.
Exactly, all vectors in z axis that are perpendicular to this. So here the orthogonal complement is basically your z axis. So what is mean by orthogonal complement? Do you understand it geometrically? So if you have a subspace, the again another space which is orthogonal to it is the orthogonal complement. So in this, I don't know whether I can really draw it well. I'll try. So let's say you are hmm, drawing in 3D. So this is your XY plane. Okay, and let's try something like this. Okay, so you are having, so if I'm calling this as X and Y, and let's call this Z. Okay, so then this is your XY plane. This is your XY plane, and your Z is kind of perpendicular to this z. Here you are having, this is the orthogonal part to this plane you are having. Okay, so you see that for this is your w and this is your w perp. You understand what is meant by orthogonal complement first of all geometrically? So the same we are putting it to words. The orthogonal complement of a subspace S denoted by S perp is a set of vectors in Fn orthogonal to all vectors in S. So here you see W perp is the set of all vectors orthogonal to all vectors in W. Okay. So in notation, you write S perp is equal to set of all u in Fn such that inner product u comma w equal to 0 for each vector in this set S. Okay, fine. Okay. And what is the significance of this complement? Okay, why is the significant? What is the significance of significance of why are complements interesting? If W star belongs to S is closest to V, then V minus W star belongs to S perp. Okay, so again, so what is this W star and what is this V minus W star? So let's look at this particular example maybe. So let us say you are having two vectors. Let us say this is your u, okay, and this is your v. Okay, now let us say this is your projection, right? This vector is your projection of u onto this vector v, right? And we have already seen that you have another vector which is here, which is u minus c times of v. This is u minus c times of v, or if you call this w star maybe. So let's call this w star so to understand it better. So let's say that this is your w star, then this is u minus w star. Okay, so you see that these two are now orthogonal. Okay, so w star is the vector which is closest to this vector. Okay, maybe here v is this one, and let's call this. So this is v, so this is v minus w star. So this is the vector v, and let's say this is your subspace S. Okay, so this entire line is your subspace S, let us say. Okay, so this w star is the closest to v on S. Then v minus w star is perpendicular to w star. Do you understand what is happening here?
Yes, ma'am.
Yeah. Okay. All right. So now S perp is a subspace of again Fn. So if S is a subspace, then S perp is also a subspace. Why is it a subspace? Okay. So for a subspace, do you all remember what are the conditions to check for a subspace?
Closed addition.
So you can say that closed under addition and closed under scalar multiplication, right? So in that case, suppose you are having, let us say, you are having two vectors u comma, or let's say s1 s2 in S perp. You want to show that s1 plus s2 is also in S perp. If they are first of all in S perp, you know that inner product u comma s1 is 0, inner product u comma s2 is equal to, or the other way around. So mm, anyway, both are same only, but I just want to follow the exact same definition. So s1 comma let's say w is equal to 0, and s2 comma w equal to 0 for all w in S, right? Now if I can show that inner product of s1 plus s2 comma w is also 0, right? Because this is simply s1 comma w plus s2 comma w. So this is again 0 for all w in S. So s1 comma s1 plus s2 belongs to S perp. Similarly, can you easily visualize that for any alpha S1, again you can bring out the alpha outside, so that will also belong to S perp, and hence it is a subspace. So these two are, so it is closed under addition as well as scalar multiplication, and hence it is a subspace. So why is it a subspace? Is it clear for everyone? Yes?
Yes, ma'am.
Okay. So the next thing is that S intersection S perp is 0. This is kind of geometrically or intuitively also you can understand, right? Suppose you are having something like a plane and then something perpendicular to it, then what is the intersecting point? It should be only the origin, right? Yeah. So
Yes, ma'am.
this is the intuition, and also you can see it using the definition. So if you take, suppose let us say you are having a vector u in S intersection S perp, then what is that, you know? Inner product u comma w equal to 0 for all w in S. So in fact, so when w is equal to u, what happens? It is true for all w in S. Specifically, u is also in S, right? So this means that inner product u comma u is also 0. So this means that u itself is 0. So this vector has to be 0. So from the definition, how we get that S intersection S purpose 0, is that clear for everyone? Yeah?
Yes, ma'am.
Okay. So what are some important properties of this complement? So regarding the dimension of S perp is equal to n minus k. Okay, so here if k is the dimension of S, then dimension of S perp is n minus k. For example, you look here, dimension of W is 2 and dimension of W perp is 1. Okay, always, for example, in R2, if you are taking one line and you are looking at the orthogonal complement, it is going to be another line passing through origin. Same way in R3, if you are going to take W as a plane, then the orthogonal complement is always a straight line. And if you are taking W as a straight line, can you tell what should be the orthogonal complement?
Ma'am, can you ask your question again?
So, okay, in R3, okay, is if W is a plane, then your W perp should be a
Orthogonal.
W perp is a line passing through origin. Okay, and if W is a line, then what can you say about W perp?
It would be a plane.
Yes, because you see that the dimension is n minus k. So here if this is 1, the dimension is 1, W perp has dimension 3 minus 1, 2, so it should be a plane. Okay, and if W is equal to entire R3, then what is W perp?
Origin.
Origin. And if W is just the origin, then what is W perp?
R3.
Okay, clear? And complement of complement is S, right? That is also again intuitively you can see. You take some vector and then draw a perpendicular. So now you say that u is perpendicular to v. Again you look at what is the vector perpendicular to v. Again you come back to the same line, right? So perpendicular of perpendicular is itself. Okay. So yeah, these are the properties of orthogonal complement. Okay.
Excuse me.
Yeah.
Why is this looking very similar to row space and null space?
Why is it looking similar to row space and null space?
Right. We had null space being, sort of the thing that will complete up the space when the row space is taken out. And now we are getting the same thing only with the orthogonality condition.
So they are the complementary subspaces of each other. That's all. So we did not call them complementary subspaces, but actually they are complementary subspaces. Specific examples. Okay, so if S is the null space, then the complementary space is the row space. Okay, fine.
Over there, we did not have the orthogonal condition there, though. And here,
Exactly.
that is what we are adding here.
Yes, yes, exactly.
Okay.
All right. Okay, so I will. Okay, the first question. Consider this space y is equal. There are quite a lot of things to cover it, so we are almost at 11 now. Okay, no problem. Consider the space y equal to 3x in R2. Find the orthogonal complement. So first, what is your W? You need to understand. So in the question 1, what's your W? W is set of all x comma y in R2 such that y is equal to 3x. Right? Note that this is a line. Right? This is a line in R2. So what should be W perp? W perp should also,
Plane.
come on, we are in R2.
Sorry, line.
Right? Again, W perp should also be a line. Okay. Now to find the orthogonal complement, you just take one vector from W. What is one vector from W? Typical vector. So you can replace y with 3x. So it is x times of 1 comma 3. Okay, so now you take, so let us say you have some vector u which is in w perp. Now let's say u is equal to u1 u2. So what is inner product of 1 comma 3 with u1 u2? So you have u1 plus 3 u2 is equal to 0, right? So which means that your 3 u2 is equal to minus u1. So if u1 is equal to 1, then what will you have? If u1 is equal to 1, then u2 is equal to
Minus
minus
3.
1 by 3. Minus 1 by 3, right? Or the other way around also you can take. So you can take the other way around. So if you take u2 equal to 1, then u1 is equal to minus 3. So your w per is basically set of all x comma y such that x plus 3y is equal to 0, or you can write x is equal to 3 minus 3y, or you can rewrite it in whatever way you want, and it is span of 1 comma minus 1 by 3. Okay, all right. So now this was in R2. Now the same thing if you are doing in R3, then you have, this is now x comma y comma z such that y is equal to 3x. Now this is a line in R3. R3. So W perp should be a W perp should be
Plane.
plane, right? So in this case, we will have two vectors spanning the plane, right? So here you have y is equal to 3x. So let us take u in W perp, and u is equal to u1, u2, u3. Okay, so you have inner product of u comma w. So a typical vector in w, let us for example say, you can have 1 3 and for example maybe 0. Okay, so any vector here that way will work. So 1 3 0 for example I am taking. So what is the vector which is orthogonal to 1 3 0? So I am taking u1 u2 u3 1 3 0. This is 0. So this means again you have u1 plus u2 is equal to u1 plus 3 u2 is equal to 0, right? Now what are all the points which are going to satisfy this? You need to take two vectors now. So let us now say for example u2 is equal to t, then what is that you will get? So u1 is equal to minus 3t, right? So the vectors you can consider here are, so 1 or minus 3 1 minus 3 1, and then let's say for example 0, and then we can take minus 3 1 and maybe 1. Okay, so now these two vectors, yeah.
And we can also write this as like bracket minus 3 u2 comma u2 comma z. Then we can write this as minus 3 u2 comma
Mm,
u2 comma 0 plus 0 0 1. So
yeah,
that we will get 2.
yeah, yeah. So anyway you can have one or one, 0 1 is just one, so one choice. Instead of 0 1 you can put any vector so that these two are linearly independent. Okay, so here so let us say this is your vector w1 and this is w2, and your w perp is span of w1 and w2. So how to find the orthogonal complement? Is it clear for everyone?
Yes, ma'am.
Only one problem here, ma'am.
Yeah.
The way we have defined W, it is not a line, I think. That is the equation for a plane. We need two of those equations and then we will have a line, I think.
Mm, okay, so let
For
me.
R3,
Yes, yes, yes.
intersection of two planes.
What you're saying makes sense. Just a minute. So here you are having x comma, yes, what you're saying is correct, because x comma this is 3 x comma z which we can actually write it as x and z in R. So we are having two variables here. I'm really sorry. This is so stupid. Sorry. Yeah. So you have that this is x times of 1 comma 3 comma 0, and sorry, x should be inside, and then plus z times of 0 comma 0 comma 1. So x and z are in R. So yes, this is actually a plane spanned by these two vectors. Yes, exactly. So one vector is 1 comma 3 comma 0, for which you get this condition u1 plus 3 u2 is equal to 0, and you also have to check the other condition. So the other condition is that, what's the other condition you have? If you are multiplying with 0, 0, 1, so if you are multiplying with 0, 0, 1, u1, u2, u3 multiplied with 0, 0, 1, I mean doing the inner product with 0, 0, 1 gives you u3 equal to 0. So in that case, you will specifically have W perp span of W1, where W1 is simply the vector minus 3 comma 1 comma 0. Okay. Yeah, so this was a really big mistake. So thank you for noticing. I hope you all understood what was the mistake here. I'm just instead of considering this as a plane, so I just took it as a line. Remember, always don't make the mistake I made. So always remember the equation for a plane is of the form ax plus by plus cz is equal to 0. So whenever you are given some set like this in R3, better you rewrite it as 3x minus y equal to 0. So immediately you remember that this is a plane, okay, and not a line. Okay. All right. So the second
Ma'am,
example.
so just like this, in the earlier question, it would be plain also. So the
Mm, no, no, no. See, here in this case, there is no z coordinate. There is no z coordinate. We are in R2. So y is equal to 3x is exactly a line in R2. But here we are in a plane. So this is the equation of a plane. Okay. And this equation, this plane is spanned by two vectors. Here this is spanned by exactly this one vector, and here we are having two vectors. See, x and z, there are two components here. So two components contributes to dimension 2. Okay, so x and z, two free variables. Okay.
okay, ma'am.
Yeah. All right. So the third problem, can I leave it as a homework? Because I have given two examples of how to find the orthogonal complement. Can I leave the third problem as a homework?
Okay, ma'am.
Yeah. So first you need to find a basis for W. So clearly W is of this form. So this is a plane in R3. So the orthogonal complement should be a line in R3. Okay. Fine. Okay. So the next thing we are going to do is moving to what are least square solution. Okay. So what are least square solution? So why do we first of all look at least square solution? So consider a system of equation Ax is equal to b. Okay, what are the possible scenarios for Ax is equal to b? What are the possible scenarios? Either it has a unique solution, or we can have infinitely many solution, or we can have no solution, right? So if we have some solution, it's fine, but when we have no solution, this is the case when we are considering, when we are going to look at the least square solution, when we really need the least square solution. In the other case also we can still compute least square, but this is the scenario where we really need a least square solution. Okay, so first we will understand what is least square solutions, and then we will see why it is called least square. Okay, fine. So this is the matrix you are having. So you are having this matrix, which is an m by n matrix representing a transformation from Rn to Rm. Okay, so and you have Ax is equal to b. You know that the solution exists if b is in the column space of A, and there is no solution if b is not in the column space of A. So in these two scenarios, you have the b in the column space, and in this scenario you have b not in the column space, it is outside the column space. Okay, so what are we trying to do now? We don't have a solution. Okay, so now what I am going to do, I am going to see what is the vector which is closest to b in the column space. What is the vector which is closest to this vector b in the column space? So if I take now a vector in the column space, I know that there is a solution, right? So I can have an approximate solution. Okay, so when there is no solution, what do? We try to approximate. Okay, find x such that ax is close to b. Okay, so again, what is mean by close? Can you go back to what we saw today and try to answer this question? What do you mean by close here?
The minimum is length, like
Yeah,
distance.
the length is minimum, exactly. So how do you get the minimum length? How do you get the minimum length? So we already have talked about what is the vector which is closest to a given vector. When, so in that case you need to do the perpendicular drop down, right? So now can you think of how to find the closest vector?
It should be something orthogonal to every other vector contained in that column space.
Yeah, yeah. Okay, so something like that. But yeah, we'll do it step by step. So the first thing is that what is that we are looking? So now what we want the distance between this b and some point here to be very small. Okay, so how are the points in the column space look? How can we represent the elements in the column space? How can we represent the element in the column space? Is set of all column space of A, set of all AX such that X is in. So here the domain is Rn, right? So hence here you have Rn. Okay, so these are the set of all vectors in column space. Okay, what I am trying to get is that I want, so what is the distance between Ax and B, which is Ax minus B. Okay, I want this distance to be minimum. Okay, I want to minimize the distance between ax and b. So that gives you the, so this gives us the closest vector to b in column space. Is that correct? Does this make sense? Okay,
Yes.
so we are looking for arc minimum norm ax minus b, x in Rn. So the vector x which gives us the minimum value. What is argmin means? The vector which gives us this minimum value. Minimum of norm of ax minus b, you know, that is the minimum value. And arc minimum means the exactly the value x which gives us this minimum value, which we will notate by give the notation x star. Okay, so x star is the value such that ax star, norm of ax star minus b is the minimum of norm of ax minus b when you vary x in Rn. Do you understand what we have written here so far? Yeah, what we are trying to do, is it clear for everyone? We are trying to minimize the norm of ax minus b. Okay, and we want to see which, for which x this norm is minimum. So far, are you with me? Yeah.
Yes, ma'am.
Okay, so for that you need to understand the concept of distance of a point from a line. So slowly we will first understand the distance of a point from a line, and then for a point from a subspace we will move slowly. Okay, so let's say you are having some line here. So a line is span of some vector u, right? And then let's say you are having a vector v. Okay, what is the distance of this point from this line? What is the distance? Okay, so the distance is given by the distance of v comma s is the norm of v minus w star, where w star is the argmin of v minus w. So argmin in the sense where this minimum is attained. Okay, so the minimum, wherever you get the minimum distance, that is the distance between the point and the line. So do you understand what is, how you define distance of a point from a line? Is that clear?
Yes.
Okay. Now, how do you obtain this W star? You know that this is the formula. But how do you obtain this W star? W star can be simply obtained by doing the inner product V comma U hat into U hat. Okay, so this is where you use the property of the inner products with cos theta and all that. So yesterday Tanzil was mentioning the exact same thing, right? So I don't think I have enough time to do this exact how we got this here, but let's do this. So we'll try to just cover the topics of today's session, and if we still have time at the end of the session, I will explain how this formula exactly came. Okay, is that fine? So it's basically something very simple. So if you have some vector mm, u, so this is, let's say maybe a and b. So what is the projection of a onto b? Okay, so you want to understand, I have to draw a perpendicular line, otherwise it looks wrong. Yeah, so you have to understand what is the perpendicular line. What, so this is, let's say b, what is the projection of a onto v? Projection of a onto b. Okay, what is the one thing you can understand? So let us say the v is the projection. Okay, if this is v, okay, what do you see the relation between b and v?
That it is a scaled version of V.
Exactly, exactly. So your V is a scalar multiple of B, right? And what is the C? The C is what you have here. Okay, and how to compute that C? That computation is involving that cos theta formula and all. So this computation of C, if you want the details, if I have time at the end of the session, I will provide the details on how we got that. Okay. So now do you understand that since this is V equal to CB, I have this formula. At least you have that idea that C is represented by this inner product. That you have, that you understand. Okay, and why instead of u I'm having u hat? Just for convenience, so I just want to consider the unit vector instead of just the vector. I want to consider the unit vector, that's all. Okay, so here this u or u by u norm, so anyway
Uh,
it's making much difference, right? Yeah, any questions so far?
Maybe here we are kind of trying to find that orthogonal vector, right?
Exactly. The vector which is orthogonal to this. Exactly. Okay. So here you see that in fact V minus W star is orthogonal to U. Okay. So this vector is the orthogonal vector. So V minus W star is orthogonal to this vector U. Okay. Fine. Okay. So this is for just a line. As I told you, this is the distance of a point from a line. Now, instead of a line, if I'm having a plane or a general subspace, then what is the formula? Okay, so in that case, you have to project this V onto the entire subspace. Okay, for which this is the formula for W star. This is the projection of V onto S. So, by the way, why did I push projection at the last? Yeah, anyway, it would have been better if I first do the projection and then this. Okay, anyway, it's fine. Okay, so this is the projection of V onto S. Okay, so this is the projection of V onto S, where S is the span of U1, U2, UK, and this is an orthonormal basis. Remember, this is a very important thing when you do the projection. Don't take any basis, always take only the orthonormal basis. Otherwise, this formula there will be some errors. Okay, you have to include some norm of U1 and all. So, if you want to use the exact same formula, always go for an orthonormal basis. Okay, so the exact same thing. So here the u is your orthonormal basis in this case, orthonormal basis of S, not u, maybe I should say u hat. So U hat is the orthonormal basis of S. Okay, because this is the normalized version. Okay, fine. So in this case also you see that here, just like we had V minus W star is orthogonal to U hat, same way you have V minus W star is orthogonal to each of the UIs. Okay, and this W star is unique. Okay, always remember the projection is always unique. This is important, that W star is unique. The projection is always unique. You cannot have several points where the minimum is obtained, right? So if you are having one line and a point, then you have exactly one point where the distance is minimum, right? You cannot have several points. So this W star is unique. Always this is unique. You cannot have different points where the minimum is obtained. Exactly one point where the minimum is obtained. Okay, that is again an important point. Okay, now let's try to understand. Okay, so we saw some theories of how to obtain this. So exactly how to obtain, here is the formula. So you have Ax is equal to B, and you know that X star is the arc minimum of norm B minus Ax, or Ax minus B, both are same, right? Now orthogonality, you have to exploit the orthogonality. What is that orthogonality? B minus Ax star is perpendicular to the column space. So let's compare this with this. Okay, so your W star here is nothing but your Ax star, and your V is your B. Okay, so this is B, this is Ax star. Okay, and what is this column space of A? So your S is your column space of A. Okay, so B minus Ax star is orthogonal to each of this ui. It means that V minus W star is orthogonal to all vectors in S. So in this case, your V is B, your W star is Ax star, and your S is simply the column space. Okay, and the column space are nothing but the span of the columns of A. So the columns of A are W1, W2, Wn. Let's call them. Okay, now B minus Ax star is orthogonal to each of this Wi. So you have the inner product as 0. Okay, so this inner product can be rewritten in this form. Do you agree that? So let's say that you are having inner product of x comma y is equal to 0. Okay, what does this mean? So let's say you have x1, x is equal to x1, x2, xn, and y is equal to y1, y2, yn. According to the usual inner product in Cn, what does inner product x comma y mean? X1 y1 bar plus x2 y2 bar plus etc. xn yn bar. Right? Yeah. So this is what you have. Now, instead of having it in this way, suppose I am writing it in this form. So I have y1 bar, y2 bar, etc. yn bar. Okay, so one rows with n columns, and then you have n rows with one column. So let's say x1, x2, xn. So this is exactly same as inner product x comma y, right? Because you are going to get again x1 y1 bar plus x2 y2 bar, etc., right? So let me not write it here. So the notation for this I'm going to give is YH. So any inner product x comma y, I can write it as YHX, where YH is simply the transpose complement or transpose conjugate. YH represents the or conjugate transpose. So inner product x comma y I can write as YHX. Is this clear for everyone? Yes.
Yes, ma'am.
So using this, I'm rewriting this inner product in this way. Okay, so when I'm rewriting in this way, what I'm getting, so I can simplify this and again rewrite it in this way. WIHAX star is equal to WIHB. Okay, so now again you can see that, so here I have to find the solution of Ax is equal to B, where so the minimum x star for which this happens. Now solving this as such is kind of see what is WIH. What is WIH?
One single row.
Yes, right. So now I'm going to combine each of this and write it together as a matrix. So now I am writing W1H AX star is equal to W1HB. Okay, so this is your W1H and here is your W. Let me change the color. So this is your W1H. So this is your I can forgot to change the color. W1HB. Same way WNHB. Okay, so each of this I am now writing everything together in the matrix form. So what is this now? I get this is the matrix AH. AH is the conjugate transpose of A. So AH star is equal to AH into B. So what is this X star? X star is basically the solution of AHA x equal to this system of linear equation. Now we have a new system of linear equation. AHAX star is equal to AHB. Okay, so from the original equation we are having this new equation. So one way you can look at it like this: how did this AH come here? So because why are we rewriting this? Yeah, so you can rewrite this in this way and you can get this. This is obviously one way. Okay, so there are several ways to obtain why this expression came and why this has a solution. There are several ways. So usually when you have a curve, how do you find the minimum of a curve? Let's say you have some function, how do you find the minimum of a function?
First derivative.
Exactly, right? So here we are trying to find the minimum of this thing. So here what you can actually do is that, so this is where the name comes from. If you want, I cannot give the entire steps here, so I can just give a hint. So what is happening? So ax minus b I want to minimize. So usually this involves some square root, right? So minimizing this as such is going to be difficult, so I am going to consider the square of this. So the minimum of this, the x for which I get the minimum value for this is the same x for which I will get the minimum of norm x minus b. So computing the minimum of ax minus b whole square makes sense, right? Because I will get rid of the square root in this case. Now this is nothing but inner product of ax minus b and ax minus b, right? So again you see that this, I can, if I use this property, then I'm going to get some h here, right? So I'm going to get ax minus b h. So first of all, anyway, you need some vectors, yeah. So into ax minus b, right? So when you expand this, you will get a function of x, right? And this function, when you find the derivative, okay, and equate it to 0, this is the equation you will get. Okay, so you know that in that case you will have a minimum. Okay, so this is another way. And why it is least square? Because the see, you see what are you doing? You are trying to find the least value of the squared term. So let us call this as y. Then what are you actually doing? You are trying to find the minimum value of the squared sums, least square sums. Okay, that is why the name least square solutions. Okay, so this is from where you get this idea of the term, the name least squares. So I have not given the entire detail, but just an outline of how this can be related to this and why the name least square. So do you get the gist of what I am trying to say here? Yes.
Yes, ma'am.
This one, sorry, is not very clear.
Okay, so here what I'm trying to say is that up to this part, is it clear? Norm ax minus b whole square is ax minus b h into ax minus b. Up to this, is it clear? Yes.
Sorry, that also is not
See,
immediately clear.
see what is, so this expression at least, is it clear? Norm of y square is inner product y comma y. That is the usual definition of norm and
That
inner.
is clear.
Okay, and then inner product x comma y is y h into x. I'm applying it here. This formula I have applied it here.
That is when we have this orthogonality and all that coming in, right? The YHX.
So yeah, this is when we are getting the conjugate transpose, not the orthogonality yet. So here we are just getting the conjugate transpose here. So the conjugate transpose, this AH comes here only. So what is this? This is AH into X minus BH. So you have to rewrite this in terms of, when doing the conjugate transpose, you can rewrite each of this term and then multiply. You will get another term here. Okay. So you will basically get a function of X here. Okay, and then you find the derivative, and the derivative is in terms of AH, the matrix AH. And then when you equate the derivative to 0, you will actually get something like, I guess it is exactly, I don't know, maybe 2 times of AHA. The derivative is like this, AHB equal to 0, and then when you equate it you will get something like this. So this is not in the lecture, I'm just giving it to understand how this minimum is obtained using the usual technique, because that is what you are already familiar with, right? So just giving an outline of how you can relate that here. Okay, so this is, I am not given the entire steps of what is this exactly and how did you compute f dash of x, but this is what will happen inside. Okay, and then here, why the name least square? I am seeking out the least value of this squared term. That is why it is least square. Now do you understand it a little bit better?
Yes, it is better. And why we are writing in terms of y1 and y2 and all that? That's simply because when we have to do the norm of a vector, we take its individual components in its basically orthonormal basis, and we square all of them up, and that's how we are writing y as y1 y2 squared whole.
Okay, okay, okay. So I understand what's your confusion here. Okay, okay, okay. Why that norm and then I write inside y1, y1. Okay, okay, fine, fine. I understand what's the problem. Okay, so here, let's say that you have any vector x norm x. So norm x square is simply x1 square plus x2 square plus etc. xn square, right? I just wrote an extra norm outside by mistake. So this is what I have written here. So suppose this is your y, the norm of this y is this, right? Do you understand?
Right, that is okay.
Yeah, so in the previous place I wrote an extra norm here. Yeah, so the norm of this term is exactly the norm of y1 square plus etc. Is exactly y1 square plus etc. yn square. So we are finding the least value of such a square term. That's all. That's why least square. Okay.
So in the end, it's just a single number, and we are
Exactly.
minimizing that.
Exactly. Okay. Our aim is not just finding the minimum value. Our aim is finding the x where we are obtaining the minimum value. Okay. So to find the x where we are obtaining the minimum value, we are solving this system of equation. Okay. So in this process, we are not finding the minimum of norm v minus w, but arg of minimum v minus w. Okay. Fine. Okay. So now the solving a system of linear equation uh, by least squares is just solving the system ax star equal to ahb. So let's try to do some problems based on this formula. So you have your a here, so this is your matrix a and this is b. So what is ah? First of all, this is just a real matrix. So in the case of real, if a is a real matrix, then you have ah is equal to simply a transpose. Okay, so what is a transpose? Again, it is in fact a symmetric matrix, so it is the same. So everyone compute what is aha. So which is actually one a square. What is a square?
5. 10, again 10, then
20, right?
yes, ma'am.
Okay, so this is your AHA. And what is AHB? So in this case, it is 1, 2, 2, 4, and B is 1, 1. So you have 1 plus 2 is 3, 2 plus 4 is 6, right? So now find the solution of AHAX is equal to AX star is equal to AHP. So you need to solve for 5, 10, 10, 20, x1, x2 equal to 3, 6. So you will get 5x1 plus 10x2 equal to 3. So this is a case where we have infinitely many solutions. So here you have x2 is equal to, so if you just say you have to put some terms for x1 and x2. So if x1 is equal to t, then what is your x2? 3 minus 5t by 10. Okay, so these are the solutions of this system. Is this fine? Just the usual way you solve system of linear equations, nothing new. Okay, so here one thing you should observe is that whether 1 comma 1 belongs to the column space. Does 1 comma 1 belong to the column space of A? Does this vector B, which is 1 1, does it belong to column space of A? Obviously it is not in the column space of A, right? So Ax equal to B has no solution. Okay, so we have found the solutions for, these are the least square solutions. Okay, now this is for question 1. So can we similarly do question 2 yourself? Can I, because this is just solving system of linear equations, right? Can I leave question 2 as a homework? Will you be able to manage to solve the system AHA equal to AHB?
Yes, ma'am.
Okay, so question 2 I am leaving it as a homework. Okay, all right.
I'm sorry.
Yeah.
Uh, have we completed the solution there? We have to minimize also, no, somewhere.
Mm, see, that is what I was trying to say. This is the solution of this system is the minimized solution. So here we have minimized the solution of AHB Sorry, I got disconnected. Let me share the screen again. Yeah. So here what are we doing? So see, this is the solution of this is the minimum point where we get the minimum value. As I told you, see if f dash of x equal to 0 at some x, then that is the point where we get the minimum of f. Is that correct?
That is okay.
Yeah. So here the solution of this system gives you the minimum value for ax minus b, norm of ax minus b. Okay, is that fine? So we have already computed the solution set here. Okay, fine.
But then we have a variable called t, right? That is what was bothering me.
Okay, so what's the problem for you here?
Like I was expecting that we'll get one proper vector as the answer. I mean, um, we'll get that vector exactly, which is the closest or one vector we'll get. So the fact that we got a set of vectors, I was kind of thinking what happened over there.
Okay, so in this case, this matrix A is actually an infinitely many solution case. So here you see that the matrix A is having both the columns or rows are not linearly independent, right? Yeah, so in this case, we are having infinitely many solution. Yes?
Geometrically speaking, let us say the 1 1 vector is a 45-degree line. The 1 2 vector, which is the column space of the matrix, is a 60-degree line. And then we have the 1 1 vector and the 1 2 vector alongside, and we can see that um, the closest thing to the 1 1 vector's head on the 1 2 line will be one certain vector. I was expecting that that is the vector that will come out as the solution. That's why I asked the question.
Yeah, so when you are, see, I understand when you are geometrically imagining, you should, what you are saying is that you should get exactly one vector, which is going to be the point where you are getting the minimum distance, right? That is what is your confusion. Is that correct?
Ah, yes, that was the question.
Okay, okay. So here in this case, so what is happening for us? So maybe let's try to geometrically visualize this. Okay. Okay, so where I don't know exactly whether I can draw this point. Maybe. Okay, so let me do one thing. After this session, I'll pull out Desmos and plot this and show you what's going on. Okay, will that be fine if I pull out Desmos and show you what's going on?
Okay, okay,
Okay.
and you'll post it in the G space and stuff.
Yes, yes, I'll do that.
Okay, thank you.
Okay, so here in the projection operator, so one now we have completed what is the what are the least square solutions. Now we are going to look at what are projections. Okay, so I guess this is the place where I should really explain why earlier we had this orthogonality, this inner product to explain to get this projection, right? So let us say you are in R2, let us say, because that is where it is easy to visualize. Okay, so this is not really looking straight line, but yeah, I'll try. Okay, so we are in R2. Let us consider two vectors. Okay, so let us say you have some vector v and some vector, or maybe a and b to avoid confusion. So let us say you are having two vectors a and b. Okay, what is the projection of a onto b? Let us call it v. So projection of a onto b is some vector v, which is actually c times of b. Up to this, is that clear? Yes, up to this, is this clear? Okay, now we have to find what is the c, right? So now what is norm v first of all? Norm v is mod c times of norm b, correct?
Yes, ma'am.
Okay, so you see that mod c is actually norm v by norm b. Okay, so this is what you have. So your v is basically norm v by norm b into b. Let us consider the positive case where c is greater than 0. Okay, so you have C is equal to norm V by norm B into B. Okay, now what is that you know about A and B cos theta, the angle, suppose this is the angle theta and this is the angle between A and B. What is cos theta? Cos theta is, so this formula I don't know whether we have explored in this course, but this is the usual formula we have. Okay, the relation which is explaining the relation between inner product and the angle. So cos theta is inner product A comma B norm A norm B. This is some formula we have, okay, which explains the angle between A and B. Okay, so now we have to kind of exploit this here. So we have a right angle triangle where this is norm V, okay, and this is norm A, and this is theta. Okay, and this is, so what is cos theta? Adjacent by hypotenuse. What is the adjacent of theta here?
Sorry, base.
Yeah, so that is norm V, right? And here you have hypotenuse, which is norm B.
Okay.
So you see that norm V, I can replace it as norm A times of cos theta, right? And what is cos theta? Cos theta is norm A into inner product A comma B by norm A norm B. So again this simplifies to, so I can cancel out this norm A norm B. So simply I have inner product A comma B by norm B. So again I can replace this term as inner product of A comma B by norm B square into B. Okay. Now this I can replace at A by B. I can bring this norm B inside. Sorry. Okay. And this is the unit vector you are having. Can you relate the expression which we saw earlier now? Right.
Yes, ma'am.
So this is exactly what we were having earlier. So where was it? Is it here or even before this? Yeah, here. W star. Sorry, where was it? Somewhere.
I think it's more.
Yeah, here. Yeah. So when we are projecting this V onto this line, this is what you are getting. So the idea comes from this understanding. Okay. So I have just roughly given this idea here to relate how we got this inner product there. Okay. So you can dig deeper if you want. Okay. So now we have to complete the remaining part. So I guess with this explanation, we will continue. Okay. So let us say you are having some subspace S, okay, and you are having a vector V. Okay, what is the a projection of V onto this subspace S? Okay, so the projection operator. So here again you have this least square concept here. So W star is the arc minimum of norm of V minus W, and V minus W star is a vector perpendicular to S. So it is there in the orthogonal complement. Okay, so the projection operator Fn onto S denoted by Ps is defined as the mapping V to W star. Okay, and it is well defined by uniqueness. Okay, so here Ps is a linear operator. So Ps is a linear operator if Ps of V1 is equal to W1 star and Ps of V2 equal to W star. How do we prove linearity? What is the condition for linearity? So Ps of AV1 plus BV2 is equal to APSV1 plus BPSV2. This is what we need to prove for linearity, right? Okay. So now what are we trying to do? So PS of AV1 plus BV2 we want to show. So we are doing some small trick here. So what is that we are doing? We are first considering. So V1 minus W1 star, we know that it is there in SPUB, and similarly V2 minus W2 star, that also we know that it is there in SPUB. So we are taking a linear combination of these two. So we know that this linear combination again is there in SPUB. Okay, and here now I'm going to just rewrite this. Okay, so if I rewrite this, what will I get? So if I rewrite this AV1 plus BV2 together, and then AW1 star plus BW2 star together, you see that if I consider this vector as U, then this is nothing but my PS of U. Okay, so PS of U is basically this vector AW1 star plus BW2 star. Okay, and what is W1 star and W2 star? If you just plug in again, what are this W1 star and W2 star? You know that this is A PS of V1 plus B PS of V2. Okay, so you have obtained the linearity. So here we just exploited the fact that V1 minus W star and V2 minus W star both are vectors in SPUB, and hence the linear combination also belongs to SPUB. In that case, we know that if this is U, then this has to be PS of U, right? Okay, so we have saw that PS, the projection is a linear operator. If the projection is a linear operator, okay, and here for this orthonormal basis for S perp, how are we going to get? So there are more properties about linear operator projection itself. Mm, okay, so here in between there is something we need to add to understand the projection operator, the matrix of the projection operator exactly. So maybe first let's see this. So what is the orthonormal basis for S perp? We know that for every subspace we have an orthonormal basis. So let us say for a subspace S, U1, U2, UK is an orthonormal basis. Okay, and we also know that if we have an orthonormal set, we can extend it to form a basis for the entire space. So let's extend this basis to form an orthonormal basis for whole Fn. Okay, now this extended the vectors which are added to extend this already existing basis, this is going to form an orthonormal basis for S perp. How? We know that already that each of this let us say V is any vector in S perp, then V is orthogonal to each of this U1, U2, UK, right? Now you know that since this is a basis, U1, U2, UK, UN is a basis, the first part of this is going to become 0, and you are having V is a linear combination of only the remaining UK plus 1 UN. Let me repeat this part again, listen carefully. What is that we are doing? First, V is a vector in Fn. So this is a basis of Fn. Okay, so I'm writing V as a linear combination of the basis vectors. Step 1. Step 2, I know that V is an element of S perp specifically. So if V is an element of S perp, what do I know? I know that inner product Vi comma Ui equal to 0 for all I equal to 1 to k, because U1 to UK is a basis for S. So this part will become 0. So what is remaining? Remaining is only the terms from k plus 1 to n, and you see that now V is a linear combination of only these n minus k vectors, and hence you know that this is forming a basis for S perp. So I take any random vector from S perp and I'm able to write it as a linear combination of these vectors. So this is a basis for S perp, and I already know that they are orthonormal. So this is an orthonormal basis for S perp. So is this part clear for everyone? Any questions in this particular discussion of orthonormal basis for S perp? Okay.
This all thing kind of got mixed up.
Okay.
Is there any
Let me
question?
let me just explain it with a small example. So let us say you are having, for example, the vectors 1 0 0 0 0 1. Okay. So now you have these two vectors. Okay, I'm going to extend this to form a basis. I can form V3 to be, let us say, 1 1 1. Okay, so now I am going to extend this. Okay, now if I am extending this, I also have to extend it such that they are orthonormal. So in this case specifically, it's better to take 0 1 0, right? Because I want orthonormality as well. Okay, so now I have S, which is span of V1, V2. Now I extend this, okay, to form, now you know that V1, V2, V3 forms a basis for R3, right? Also, I know that this extended vector V3 is going to be a orthonormal basis. So this is an orthonormal basis. Orthonormal basis for S perp. Okay, so if you just extend the given basis to a basis for the whole space, the new set of vectors added will be the orthonormal basis for S perp. That is what is mentioned here. Is it clear now?
Yes, ma'am.
Okay. So now using this, how are we going to find the matrix of the projection operator? Okay. So let us say you have some orthonormal basis for S and you have an orthonormal basis extended from this to form a basis for Fn. Okay. Now how are we going to find the projection of any vector? So you know that any vector V can be written as a linear combination of this basis vectors using this formula. We already know, right? And then since this u1, u2, uk forms a basis for S, the first part belongs to S and the second part belongs to S perp, right? Now, if PS of V I'm doing, I want to project this vector on S, what happens to this part on S perp? First of all, before this, I'm asking a general question to all of you. Let us say you are having some subspace S. I am projecting some vector onto the subspace S. Where will the projection lie? It should obviously lie on
S.
yes, right? So that is one important thing you should remember. So PS of V always belongs to S. That you should remember, right? Because this is the projection of V onto S. So now PS of V is a vector in S. So you see that it should be a linear combination of U1, U2, UK, right? And this part, when you do the projection, this automatically becomes 0. Okay, the part of this S perp automatically becomes 0. Okay, because this part is from S perp. Okay, so what happens to the vectors in the S perp? When you project this part, it will just go to the 0 vector, right? So PS of this part will go to the 0 vector, right? So for example, what is the, so I'm asking some very basic questions to see your understanding of projection. What is the projection of this vector 1 0 0 onto S? I am projecting a vector in S.
011.
Yes. Sorry.
Zero one one.
Y011. You are projecting onto S, so it should be in S only, right? It cannot go out of S. That's what I was discussing here also. PS of V should always be in S. So what is PS of 100?
And multiple
Same
of
thing.
this.
No, 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 no. It's exactly the same vector. See, this is your vector V. You want to project this vector onto V itself. So you are getting the same vector. You are not doing any change here. Okay. Next,
Okay.
what is PS of V3? Remember, V3 is an
Wait.
orthonormal basis for S perp. And you know that V3 is or so if this is your S, this V3 is perpendicular to S. So what is PS of V3?
Zero.
Exactly. This should be the zero vector. So what is the takeaway, main takeaway here? So PS of V is V if V belongs to S. And PS of V equal to 0 if V belongs to S perp. Okay. So with this, now can you understand this better? So PS of V, so let us call this first part as maybe V1. This part let us call it as V1 and this part as V2. You know that V1 belongs to S and V2 belongs to S perp. So PS of V is equal to PS of V1 plus PS of V2, right? And PS of V1 is simply V1 and PS of V2 is 0. So it is again V1. Do you understand what is PS of V now? Yes?
Yes, ma'am.
Okay, now I am going to simply rewrite this V comma U1 as U1HV and VUK as UKHV. So each of this inner product I am rewriting as scalars here. Okay, and then again I'm doing more rearrangement. So I'm going to rewrite it as U1 U1HV plus etc UK UKHV. Okay, so now you see that again I'm using associativity and changing the brackets. So this is what I'm getting finally, and this is the matrix representation of, so this is what is here. So PS of V is equal to, let's call this, I don't know, some AV. So where A is this matrix. So to find the matrix representation of PS, you need to look at the orthonormal basis of S and then you have to compute this. That's all. Okay, fine. So what are the properties of the projection operator? If PS is a projection, you know that PSU equal to U for all U in S, right? So in PS of W equal to 0 for all W in S perp. Okay, and what is the range of PS? Since any PS of V, so for any V in Fn, PS of V always belongs to S. So this means that range of PS is equal to S, right? And what should be the null? Null of PS should be S perp, because you, if you project any vector from S perp, that is going to 0. So from here you can see that null of PS is S perp. Okay, and PS square equal to PS. Why is that so? Why is that so? So let us take any V in Fn. Okay, so PSV is some, let's say U, and this U is already in S. And what do you know for an element in S? So if I'm applying PS again, so PS of U is again U. And what is PS of U? It is nothing but PS square of V. So PS square of V is same as PS of V. So PS square equal to PS. So why PS square equal to PS? Is that clear for everyone?
Yes, ma'am.
Okay. Okay, so we are almost at the end of the session. I'll just do one problem so that you understand how to compute this projection operator clearly. So first step is that you have to orthonormalize this. Okay, so first step is that, so step 1, so use Gram-Schmidt and find orthonormal basis. Okay, step 2, so let us say the orthonormal basis you have obtained is U1 U2. Then for finding the projection operator P, you simply, let's compute the matrix first, the matrix of P, so which is, maybe I'm denoting with AP. Okay, so AP is U1 U1 transpose plus U2 U2 transpose, because it is just all real numbers. These are the two things you have to do here. Okay, so since we are running out of time, what I will do is that I will give you the answer for the first question. Okay, and then you can verify. For the first question, the orthonormal basis, so for the first vector, you know that you can simply do the, so let's say this is v1 and v2. So for the first question, your u1 is first of all 1 by root 2 times of 101, and your u2 is minus 121 by root 6.
1
Minus,
by root 14.
so if I do minus 1 plus 1, 0. Yeah. So this is an orthonormal basis. So this is U1, U2. Now how do I find the matrix P? The projection of, so the AP. So U1, U1 transpose plus U2, U2 transpose. So what you have to do? 1 by 2 I can bring out commonly. So 1 by root 2 into 1 by root 2, 1 by 2. So 101, and then again I multiply it 101, and then same 1 by 6 into, I have minus 1 to 1, and then minus 1 to 1. Okay, so you will have a matrix 3 cross 3 matrix here. So if you want the 3 cross 3 matrix, so
Maybe we
And
should
I think it
multiply
will be
the
scalar.
Yeah, so you just have to multiply and bring it here. So you, I guess I can leave this to you, just computing, right? So I can leave this to you. So if you want to verify the answer, maybe you can do the verification in the TA session also. Okay, so what is the procedure to find the projection operator? That is clear to you, right? Yeah.
Yes,
Okay.
ma'am. By the way, I think that will be scalar because the first matrix is 1 cross 3 and the second one is 3 cross 1.
See, no, 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 no. This is okay. I have written it in the wrong way. So maybe if I rewrite, then you can see that this is not a scalar.
If the U1 transpose would be on the first,
I
then
have to rewrite it this way. Sorry. So now it will make sense. Okay. So now you see that this is a 3 cross 1 and this is a 1 cross 3 and same here. So you will end up in a 3 cross 3 matrix. So the projection operator, whatever you are getting here, you will see that that will always, when you multiply it with these vectors, you will get the same vectors. Okay, all these properties you can observe. So once you compute the answer, I recommend you to try and do these things. Okay, observe the following properties. So you try, let's say, AP of what is u1, you should get again u1. Okay, and what is AP of u2, you should get u2. And then let's say that u3 belongs to s perp, then AP of u3 is 0 times of u3. Okay, so even from here you get an idea of the eigenvalues. What are the eigenvalues of any projection operator? What are the eigenvalues of?
Either 1 or 0.
Exactly. And the eigenvalues 1 corresponds to the basis of the space S. The eigenvectors of 1 corresponds to the basis of the space S. And the eigenvector corresponding to 0 corresponds to the basis of S perp. Okay, so this is some important observation you have here. Okay, and also you can see that because of this also ps square is equal to ps, right? So what does that mean? Ps square is equal to ps means, so you have ap square equal to ap. So from here also you can see that determinant of ap square is equal to determinant of ap. So this means that your determinant is either, so here, okay, so one thing you can see, determinant is 0 first of all. So not this, so maybe I should write ap square minus ap. So ap square minus ap equal to 0. So ap into ap minus I equal to 0. So from here also you can note that the eigenvalues are 0 and 1. Okay, fine. So these are the main properties of projection operators. So I hope I have covered all the important things be required for week 10. Are there any questions in today's topics? So in today's session we have covered Gram-Schmidt orthonormalization properties, and then we also covered what are projections, and then we also saw least square solutions, right? So all these things we have covered today. So orthogonal complements, right? These are the topics we have covered today. Any questions? Okay, so
Excuse me,
yes,
just if you have a couple of minutes, I wanted to ask about the possible logistics.
yes.
We have gone through a whole lot of things today, and we have tried very hard to get through the sheet, but I think 5 pages still remained at the end.
No, 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 no. They are just some empty sheets, I guess. So I have tried to complete everything. So this page I have to complete these problems here, but I don't have enough time to do the problems. They are just some empty papers only. I have completed what I intended to as much as possible. Yeah.
Okay. Then the other suggestion I would make is, could you please ask our TA, Mr. Anant Kumar,
Hmm.
to do a short recap of these 10 pages when he starts his TA session? Meaning we can have other things in the TA session, but he
Okay.
can begin with a recap of this. So we can spend maybe half an hour or something, some reasonable amount of time going over this sheet again, because this is a whole lot to take in, honestly.
Sure, I can definitely ask Anand. Or, in fact, what you can do, you just right after the session, you can put a message in the group asking Anand to cover a make a quick recap of today's session before starting the tomorrow session, or tomorrow, or when is the next session. I don't remember. So before the next session, okay. So I'll tell Anand. No problem. Any other question or request you have, suggestion you have? Okay, so then we'll see again in the next session then. Okay. Okay, so since there are very few more sessions left, there are three students here still. So let me just quickly ask the following. So you have been attending my sessions from week one. So I just wanted to ask quick feedback. So what are the things